I look up and I look down, and I chill with awe. I look up to the universe and envision hundreds of billions of galaxies going on and on and on, perhaps forever. I look down to the atom and imagine minuscule lengths, a billionth, 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 billionth of a meter. These are not the fringe of reality. These are the core of reality. The universe and the atom are the most fundamental facts of our physical existence. They are breathtaking. I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out why. The universe is breathtaking, but why is this so? I start with its fundamental structure, how the universe is put together. I go to MIT to meet Nobel laureate Frank Wilczek, who unraveled the inner structure of atomic particles. Frank is a literate expositor of the meaning of physics. We meet in his Cambridge home. Frank, you've said that physics is triumphant, it's exciting, and it's a
mess.
Why is it a mess?
Well, it's a mess because our ambitions are so high. We've managed to explain so much in terms of elegant equations that we think we should be able to close the deal, explain everything in terms of elegant, simple equations. And maybe we will, but at the moment, the equations of physics have many loose ends.
You've also talked about this word that pops up among scientists, philosophers, reductionism.
Well, I hate that word. I don't like the word reductionism. I much prefer what Newton, who in many ways started it all off, called it, which is analysis and synthesis. And it's the idea that to understand natural phenomena, the procedure, or a procedure you might try, is to study the interactions among small bits and try to find if you can find simplicity in those interactions, and then build up by saying that the big things are just governed by the laws of all the individual small things added up without anything else. We have been extremely successful in understanding the interactions among elementary entities in the sense that we've found elegant, simple equations for their behavior, and that using those equations, when you build up to describe more complicated things, you don't have to add anything else. People work very hard to try to find things that are discrepant, but they haven't succeeded. And people look for vital forces in biology. They look for essentially chemical laws. None of that has turned out to be fruitful. Fortunately, I don't think it's reduction in the sense of making things less. It gives you wonderful new insights, because when you do the synthesis part, you find surprises. You find that having this underlying knowledge of the way things work allows you to make complicated circuits, allows you to make computers, allows you to make lasers, allows you all these surprising things that by naive fumbling around you never ever would have produced.
As you are so fascinated by this, are you digging into the really fundamental nature of reality and seeing physics as being descriptive of the most fundamental aspects of what's real?
Fundamental, the meaning of the word is that you can't explain it in terms of anything simpler. And we may get to that. And in fact, I think a lot of the most interesting science belongs to the synthesis part. That's where you have to use your imagination to see how to use the concepts, to use the basic irreducible knowledge to do useful things or understand strange phenomena. It's a tremendously creative process. It definitely is fundamental in the sense of good. You learn things that are pleasing and useful and just wonderful.
How remarkable to reach so deeply into the essence of matter, the excitement of fundamental physics, finding the simplest, most basic structures or forces or laws. Analysis breaks the world down into its component parts, and synthesis builds it back up into its splendid diversity. How awesome to comprehend the universe, the very largest thing, by comprehending atoms, the very smallest things. To appreciate this astonishing relationship, this intimate causal connection between largest and smallest, I visit Nobel laureate Steven Weinberg, a founder of the Standard Model of particle physics. Steve, what is it about the structure of reality which demands that in order for us to understand cosmology, we must understand subatomic particles and forces, which are the very smallest components of reality?
Well, just as in everyday life, we want to know where we come from, what was at the beginning, or at least at some very early time. And we know the universe is getting cooler. It's getting cooler because it's expanding. So it was once much hotter. And when you go back to very early times, when the universe was a millionth of a second old, the universe was so hot that particles banging into each other just from their heat had enough energy to produce exotic particles that don't exist anywhere in the universe today, and we can't understand what was going on at those very early times. Without knowing more about these particles, we need more information about them in order to be able to trace the universe back to its roots.
So, to understand fundamental physics, what are the areas that we must begin to understand? Space-time, energy matter, forces.
Well, we have a good working theory of space and time, Einstein's general theory of relativity. We have a good framework for the understanding of elementary particles, atoms, nuclei. It's called quantum mechanics, which was developed in the 1920s. They don't work well together. When you apply quantum mechanics to space and time, including gravity, which is an aspect of space and time, you get mathematical inconsistencies. I would say that's big problem number one. We have to be able to understand space, time, and gravity in the language of quantum mechanics that we use to understand electrons and atomic nuclei.
Tell me a little bit about quantum mechanics, because that really underlies all theory of fundamental physics.
Quantum mechanics is the language of fundamental physics. It's the essential intellectual framework of physics. In quantum mechanics, you don't describe nature in terms of just particles banging into each other, but instead, the quantity which quantum mechanics focuses on is something called a wave function, which describes not where particles are at any given instant, but what are the probabilities. Probabilities of what? Well, it depends what you ask. If you ask what's the probability of finding a particle in a certain region of space and time, then doing certain mathematical operations on the wave function will tell you that. But if you ask what's the probability of a particle having a certain speed, then again, we know how to use the wave function and calculate that. The wave function evolves deterministically. That is, if you know what it is at one moment, you know what it is at any future moment. The wave function just evolves on like Old Man River. It keeps on going, moving, and in a perfectly deterministic way. And it's only when human beings ask questions in the old-fashioned language of classical physics, like where is the electron?
Like a billiard ball.
Yeah, or where is the billiard ball? Or how fast is it moving? Using the wave function, you only get information about probabilities. To understand the particles that make up the universe, we have to talk about quantum mechanics. When we study what the universe was like when it was a millionth of a second old, and we want to know how the particles were distributed in speed and position, we must use quantum mechanics to analyze that. The universe, on the other hand, is pretty big, and big things like tables and chairs and the universe are very well approximately described in the old-fashioned language of classical mechanics. And quantum mechanics has not yet been successfully applied to the whole universe. That's a big question. How do you describe the whole universe in the language of... Is there such a thing as a wave function of the universe? Now, what do you mean when you do experiments on the whole universe? Who's going to do those experiments?
Quantum mechanics, the dual nature of reality as waves and particles, all accessed by probabilities and observations. It seems absurd, but it is real. Our cosmos is strange indeed. And such strangeness is not an oddity. No, quantum strangeness is a fundamental building block of reality. That's what's so breathtaking. But how to penetrate the veil of quantum mechanics? It's so counterintuitive. I go to Iceland, to a gathering of the Foundational Questions Institute, where I meet David Finklestein, a pioneer in the field.
The starting point for me was this understanding that quantum theory forces you to give up the old logic and replace it by a new one. The simplest way I have of understanding the new logic is that you really turn your attention away from objects toward processes.
So process is more fundamental than object.
That's the way I've had to think about it, simply because quantum theory is almost entirely a language of processes. It's full of things called operators, and oddly enough, they represent operations. All we ever talk about are the operations. So this replaces the old kind of object ontology by what might be called a process ontology, but that's almost a contradiction in terms, because ontology is about being and process is about doing. When I presented some of these views at a conference at Columbia, one of the participants, Dalai Lama, took to calling me Mr. Actuality, because I'm happy to say things are actual when I'm unhappy to say they're real.
Okay, define
Because
it.
of the root, actual, act. Actual is what's going on, not what is.
And so therefore, the word actual has more of a
Doesn't bother
process
me a bit.
field,
Exactly.
whereas real has a more of a static permanence.
One of the big traps is objectification, and calling things real tends to make you think they're real. And calling them actual, I find safer.
But does that really mean that the objects are really not real, or just as you should now pay more attention to the process as opposed to the object?
If you look into what people mean when they say that things are real, it turns out, whether they know it or not, they're saying they obey ordinary logic. Either A or not A. They apply ordinary logic to real things. Saying they're real means you don't have to worry about what happens to them when you know about them. You just know them as they are. And that's all bad news for quantum mechanics.
You can get into a notion where everything sort of dissolves if you think too hard about it.
Unless you focus on the actions. And even there, you have to give up trying to say too much about yourself. Just say what you know. And you can get away with ordinary language as long as you're talking about ordinary actions.
And then from this, you're actually predicting real results that is very quantitative, very predictable, and very certain that are real results.
I would say that quantum theory is the most practical physics there is.
This is the bizarre nature of quantum mechanics, the logic of actions, not of objects. Actualities, not realities. This is how the world works fundamentally. Only by being wild and weird at the atomic level can the world be ordinary and normal at the human level. That's what's so breathtaking. So the more we understand what's fundamental, the more we appreciate what's breathtaking. That's why I'm back at MIT, to speak with Seth Lloyd, a pioneer in quantum computing. Seth, what does it really mean to say physics is fundamental?
The laws of physics are supposed to apply to everything, everywhere, without qualification, without any accidental historical data thrown in. Compared, for instance, with the laws of biology, there's billions of years of historical accidents that went into creating the human genome the way it is. Hey, some little gerbil-like creature gets stepped on by a dinosaur, hundreds of millions of years ago, and we're not here, right? That means that at some level, biology is not completely fundamental because the laws of biology involve all sorts of historical accidents. So the laws of physics have this claim that they apply everywhere. You're not just on Earth, maybe not just in our solar system or a galaxy, and maybe not even in our branch of the universe, right? Because many people, including me, believe that the universe is there's not just one, but there's a multiverse, a whole collection of possible universes.
Right.
And the laws of physics are supposed to apply everywhere there as well.
Now, the aspects of those laws in different multiverses are supposed to be changeable. I mean, the different constants of physics, the whole laws of physics can be different in different multiverses, depends on the theory by which they're generated.
Absolutely. And in fact, does
that make them less fundamental?
Well, yeah, it raises some pretty interesting issues, yeah. So, for instance, I have this pet idea I call a complexor. A complexor is a system that can compute, so that's the first thing, it's a computer, can do computation. But in addition to being able to compute, this complexor systematically explores all possible computations. In this branch of the multiverse, we explore one, in this other branch, we explore another. So there's this complexor has a set of rules by which it evolves. We could call them physical laws. But the funny thing about this is that you can't tell from looking at a complexor what is fundamental. The reason that you can prove that a complexor will generate all sorts of other things is that the thing that makes a computer universal, that makes it capable of computation, is it can be programmed to simulate other computers, more complicated computers, which then in turn can be programmed to simulate other computers, which can in turn be programmed to simulate the thing you started out with. So there's no fundamental level here, and this complexor, because it's systematically exploring everything, well, it's exploring all possible ways of generating complexity in one way. It explores all possible ways of generating complexity in another, which in turn explore the original way of generating complexity you have. There's no bottom, right? So in some sense, the notion that some things are more fundamental than others might be an illusion, and it might simply be that what we call fundamental is another computer's complex.
Fundamental is wherever explanations stop permanently. If we find a fundamental, we broaden breathtaking. But what many think obvious, what I think obvious, one very smart fellow thinks wrong. That's why I head to Princeton, to the Institute for Advanced Study, to meet Freeman Dyson, one of humanity's most innovative and provocative thinkers. I do not expect Freeman to amen the conventional chorus that fundamental is the holy grail of science.
I hate the word fundamental. That's one thing I've not been chasing after in my career as a scientist. I love details. I like to look at a real thing and try to understand it. I don't give a damn whether it's fundamental or not. It happens that physics has a sort of reputation of being fundamental, which I think is mostly a fake. So to me, those are not important questions. The important things are just the details. What wonderful things are out there, and how subtle and beautiful are the tools we've invented. I mean, science to me is about tools, not about concepts.
Why do so many fundamental physicists, as they're called, take such pride in their fundamentalism?
Well, there are different kinds of people. Fortunately, we need different kinds of people. I'm a frog and they're a bird. That's roughly the classification that I use. I mean, birds are the people who fly high and look out over the landscape, and they are, of course, very proud of being fundamental. But the frogs, meanwhile, live in the mud and actually study the flowers and find out what's really going on.
What are some of the beautiful flowers that you've seen in your career?
Basically, I'm a mathematician, so my tools are essentially calculations. And the most beautiful things I've done actually are pure mathematics, which have nothing to do with physics. I mean, I discovered a beautiful theorem concerning sequences of integers which only about 3 people in the world ever understood or were interested in. Mathematics is full of gems like that, and physics is too. So another thing I did was a subject called random matrices, which I did 45 years ago, and the main reason that it was supposed to be interesting was that Eugene Wigner, who was a great physicist who lived here in Princeton, thought it was a way of looking at nuclei. Well, there's really nothing fundamental about it. It's an example just where an elegant mathematical tool can actually teach us a great deal. And this is, of course, the great mystery that why is mathematics so effective?
That itself is a fundamental reality.
You can call it fundamental if you like. It's real anyway.
Whatever ultimate explanations may be, how quantum mechanics constructs reality is breathtaking. But that's the micro world. What about the macro world, the mega macro world? I go to Berkeley to meet one of my heroes, Saul Perlmutter, who discovered that the expansion of the universe was not slowing down due to gravity, as everyone had expected, but was rather speeding up. His is one of the most shocking discoveries ever made.
I have a little sister who, when I first started talking to her about the scale of the universe and the size of things, she started saying, "Stop talking about that. I just find it too creepy. I don't even to think about the scale of the universe because it's daunting. I mean, it's the distances just to the nearest star are immense by human scale, and that's the nearest star. And then you go out to the nearest galaxy, and then you go out to the cluster of galaxies. I mean, the whole thing is just beyond our brain's capability of feeling significant when you think of these scales.
Actually, creepy is a pretty good word. I mean, I think I feel that way too.
So she just found disturbing, but for me, the funny thing is that I realized I sort of thought about that. And I thought, well, why don't I find that creepy and disturbing? And I realized it was partly because, for me, you end up starting to feel like you are in a very nice middle position in this gigantic world. That there's a world of things that are bigger than us and bigger than you can possibly imagine, but there's a world of things that are smaller than us and smaller than you can possibly imagine, and somehow we're in this kind of nice cozy middle, looking out and looking in and trying to understand where we fit in this
and able to understand both.
Well, precisely, and the fact that we even get these little glimmers of a way of picturing what this world is that we live in, I find astonishing. There's no guarantee at all. Nobody promised us that we would evolve brains that are able to work in this particular Earth that we live in, that could also understand any of the stuff that's that much bigger than us or that much smaller than us. And yet, surprisingly enough, we've evolved brains that seem to be flexible enough to abstract things out and start asking questions about those things. And to me, that's remarkable. And so there's something very satisfying about being in this position of being able to ask these sorts of deep and big questions.
And when we are in this middle, which is a wonderful way to look at it and look at both ends, we then now see that in order to understand each of the ends on radically different orders of magnitude scales, we need to combine them.
No, that's right. I mean, that was even more remarkable. that the tiniest things that we could possibly imagine that we are trying to develop theories for tell us things about the very biggest things that you could possibly imagine that shape the entire universe, and vice versa. There's so much interaction that it does start to make you feel like you're living in a more coherent whole than you might have expected. And once more, I always feel surprised because there's no reason it had to come out this way.
We humans stand roughly midway between atoms and galaxies, apprehending both, appreciating both. From the weirdness of quantum mechanics describing every particle, to the astonishing accelerating expansion of the entire universe, fundamental and breathtaking in both directions, looking up and looking down. How things work on the grandest of scales and on the most minute of scales seems so far removed from ordinary life. But ordinary life is the anomaly. We are what's strange. The universe and the atom, they are what's ordinary. I think about knowing all of this, all so quickly, all in a few thousand years of recorded history, even while most human effort was wasted on war. All in a few hundred years of real science. Some say the more we comprehend, the less the mystery. Not me. I say the more we comprehend, the greater the mystery. I bet there's a reason, some kind of reason, that's closer to truth.
For complete interviews and for further information, please visit closertotruth.com.